Okay, last week of the semester, several announcements. First, some of you have a final conflict with blockchain class, and I believe we solved that issue. If you have other conflict, let me know as soon as possible. Then, if everyone submits the course review, the same policy. If everyone submit 90% of you submit the course review, you get some bonus points. Then homework 6 has been released this morning. I give you 10 days, but since it's the final week, if you need another 2-3 days, it's okay. So this one, there will be no late penalty. But of course, we are taking AI violations seriously this semester. Many students, I don't know, maybe 8, have got a penalty for AI violations. One or 2 failed the class because of that. So I will give you extra days if you need, but do not violate AI. Then anything else? Okay, so today will be our last lecture. So Wednesday, we're going to have a review of this semester. Cool. Today, we will talk about web security, another very important piece of modern cybersecurity. Web security itself, it's also a big topic. It deserves its own class for a whole semester, just like software security and network security. Some people would argue web security is part of software security because web is basically also software, but web is getting so big, it should have its own class. So we would say web is part of the internet, is a subnet of the internet. When we talk about web, we're mainly talking about all the systems using the HTTP protocol and also HTML, those kind of stuff. So there are a lot of systems in our internet. We're not really using HTTP or HTTPS. They are technically not part of the web. So web was developed back in the end of the 80s. Tim Berners-Lee, so he basically invented the World Wide Web, 3W, and he was thinking about developing information management system, so we can transfer in text, graphics simultaneously at that time, and it was a client-server data transfer protocol. And then to facilitate that protocol, he also invented a markup language, which is what we know today as the HTML. So I think this is his original proposal. You can see the title. The original proposal was information management proposal. So it's an information management system. And he was working at CERN at that time. I believe it's a physics, something, a facility, research facility. And his manager believed the proposal was vague at the time, but also very exciting. So asked him to move forward with his proposal. And this thing eventually becomes so big that a lot of what we are doing online right now, even though not all of it, but a lot of it is part of the web. Well, basically right now you can do anything with the web, right? You can, previously, if you want to change a picture, you use a Photoshop, whatever. Now there is an online version of Photoshop. You just do that on your browser. For my software security class, you can do that in the browser. If you want to watch video, dramas, you go Netflix and all of this. You don't need to install your own standalone software application. You just use your browser, and the browser will use HTTP, HTTPS, and that is part of the web. So basically right now, just within web, you can do anything you want. So back in the 90s, web has 3 fundamental technologies that still is the foundation of today's web. The first one is HTML, the hypertext markup language. Basically, this is the format language for the web pages, and that's the format language for the web. Then is the uniform resource identifier. This is the address which is unique to a resource on the web. The domain name we talked in the network security modules can be part of UI. Then we have the HTTP, which is an application level protocol. HTTP usually will be used on top of TCP, but it itself is an application level protocol. So Tim also developed the first web page editor, browser, and also the first web server, HTTPD. We are still using HTTPD today for some of the Linux systems. So HTML, some of you probably programmed this before. I'm not sure if I should use the word program, because this is not really a programming language. It's a markup language. So this is language you use to create a structured document. You can embed images, objects, forms in this language. HTTP is this application protocol within the client and the server model. So because there is a client, there is a server, which means the client sends request and the server replies or responds to that request. So this is a basic mechanism for web applications. The client initiates a request and the server responds to that. And when server, what does the server respond? Very likely to be in HTML format. It could be also other format as well. So here is one example. We have a client and we have a server. The client sends a HTTP request. Because HTTP, like I said, this is an application level protocol. So when we go down in the network protocol stack, we try to save as a overhead. We want to encode all those commands. We want to encode all the protocol headers, right? So for example, if your IP address, we only use IP address is 32 bits, IPv4. 4 bytes, 32 bit. We don't write the IP address as the digits. We encode them using hex to write the IP address. However, when at the application level, we don't really care about the size that much. We just use plain text English to do a lot of things. So the HTTP protocol, the commands are just plain text English. So when you visit a website, your browser sends a HTTP GET request, and that request, the header is just the plain text English GET. Then it has the web page they want to use and the protocol we want to use. In this case, we're using HTTP 1.1 protocol. Then after that, the header will just include all kinds of other information, and all of them were just plain text English, like the host. We're trying to access example.com. The web browser we are using from the client side is a Mozilla 5.0. Then the browser will accept HTML and XML. The language will be English. The encoding will be gzip, collection, keep alive, those kind of things. All of them just plain text English. Different from the lower layers like TCP, we use one bit, several bits to indicate things. Then the response is also plain text English. The response first say what protocol this is. This is HTTP. Then after that, there is an error code or error message. In this case, there's no error, so it's a 200 OK. You always say other kinds of error message, like a 404, the page doesn't exist. 431, the collection is reset, something like that. But 200 is basically just everything is good. Then there is date. There are all kind of headers. Then after that would be just the content. The content in this case is just HTML. The HTML has its own headers, has its own body. So all of this is just in plain text English. So in the early days of the web, obviously the web pages, they were just static, which means there is a web developer, webmaster. So they just publish static text on the website. They do not change them very often, and also those content, they were not dynamically generated. So to do that, you just need to know how to run a HTTP server and also just code in HTML. So those are just the static websites. For example, we have a browser here, a server. The browser say I want to visit this vacation.html. Then the browser will send that HTTP GET message to the server. Then the server will just retrieve. The server will just retrieve the web page of vacation.html from its hard disk. Maybe in this vacation.html, there are some embedded pictures. Those are embedded pictures. They are not really part of this file, HTML file. They are separate files. The HTML file basically points to that images. Then the server will retrieve all those related files and send them back to the browser, so the browser can display everything based on the structure. There is a header, there is a body, there is some text, then there are some related pictures associated with that text. The browser will develop that, will just display that or render that. Because the HTML is a markup language and it links to many different files. So when our browser visit a web page, even though from the user's point of view, that is just one web page, the browser may make many HTTP requests, not just one request. It will first visit that main HTML file. If that file points to other videos, audios, pictures, then browser may send extra HTTP request to get those resources and eventually display them. So different from the previous picture, previous example, where the server prepares the HTML and also the picture, both of them, and sends them back to the server. What happens right now may be different. It's like the browser will just send a HTTP message, get message, get a vacation.html, and the server will just return that using HTTP response, vacation.html. Then the browser will pass that HTML and realize, oh, there is a style file for this to tell me how should I render this. And that is in styles.css. Then the browser will send another HTTP GET message to retrieve that. Actually, the styles.css or any other resources, they may not be on the same web server as the vacation.html. They could be on different servers, right? So that's why the server, sometimes, they cannot just send them back in the first place because the server do not really have those data. Those resources may be on other servers. Then the browser keep passing the file, realize, oh, I should display a picture here. And the picture's address is this. Then send another HTTP GET message to this web server, or maybe another web server to retrieve that. And those servers will return it back. Then the browser will collect all the resources and render them, display them to the user. So because of that, developing browser, at least 10 years ago, was a very, very hot area. Right now, it's very mature. 10 years ago, it was a big arena for big companies to develop browsers, because a browser is the portal for the web, also for the internet. If people use your browser, then they do everything with your product. And developing browser is actually a very, very challenging task. Browser itself becomes an operating system, because on top of browser, you also run all kinds of applications. The website, they include JavaScript. The JavaScript is a program. So your browser need to provide an environment to run those JavaScript, and the JavaScript could be malicious. A user may visit all kinds of websites. They have code to execute on the user's computer, on the user's browser. So how do we isolate those JavaScripts and also at the same time run them in a very fast manner? So those were research and engineering areas in the past 20 years, I would say. So HTTP request, we have two types of request. We have HTTP GET request. We also have HTTP POST request. The difference is HTTP GET request. Then this one, you can have basically you have all the information like parameters, the full link, everything at the address. If you type something in your browser address bar, you type it there, you are sending a HTTP GET message. And that address, you can type all kinds of parameters there as well, and you can bookmark that, right? For post messages, those information are not in the address. They are in the HTTP headers. You can still have those parameters, but those parameters will not be part of the address. They will only be part of the header. Since they are not part of the address, your browser will not be able to bookmark that. The forms, usually we can use a post method. To visit a web page, a link, you can use GET method. But both methods can do many similar things, actually. Then back in the 95, we started to have dynamic websites. What that means is the web pages, they are not just HTML, or they are just a static HTML. When a user, a browser, send a HTTP request to the server may dynamically generate the web page, dynamically generate the HTML. Of course, I mean, you do not dynamically generate the full HTML from scratch. Some part of them is dynamically generated. Other part are just templates, right? To do that, so you do not only run a web server that listen to web requests and send out messages back. The web server also needs to run some code, need to pass the request from the user and run some code. That's when we had the server-side programming. PHP is still one of the most popular languages for the server side. I believe many of you used this. So after we have a server-side programming, the request goes to the web server. Then instead of directly retrieving a HTML page, the PHP language, the PHP code will execute, generate a HTML page, and that HTML page will be sent back to the browser. So the browser, the user doesn't directly say the PHP code, but they say what the PHP code generates. So that's the beginning of server-side programming. Then also near that time, we had a client-side programming as well. And JavaScript is the language for client-side programming. In recent years, we have some new languages like WebAssembly. No, I think WebAssembly probably is, no one probably direct code in WebAssembly. But all other languages can be compiled into WebAssembly. So JavaScript is still the language to run at the client side. So by saying that, it means the browser needs to provide an environment. That's why I say browser right now itself is like an operating system. On top of browser, you run programs. And those programs could be JavaScript. Then the JavaScript running on the browser side can manipulate the web page, and they can also send and receive HTTP request, especially using the mechanism called AJAX in synchronous JavaScript and XML. So basically, you don't have to reload the full page. The JavaScript inside one page can retrieve something from the server and update partially of a web page. Doesn't have to. It's not like refreshing the whole web page. So this is just one example of JavaScript. You use the script tag, then you define a function, my function here, then a document points to the current document, the current web page. Then from there, you can retrieve the one element whose name is demo. Then after that, you can change the HTML text inside that. This is what this piece of script does. Of course, this can get very complicated to all kinds of crazy stuff. So then, what kind of security problems we have for this kind of web setup? As we said that, to think about what kind of security problems we have here, you need to think the layers of computing components we have here, right? So basically, we still have the operating system. On top of the operating system, we run browsers. Browser itself is a program usually developed by using C or C++, which means the browser itself could have a lot of software security problems. Then on top of that, we run JavaScript. Actually, the JavaScript, they can come from many different websites. So your browser may have many tabs right now. You are visiting many different websites at the same time. And all those websites at the same time, simultaneously, they are running code on your browser. Okay? So this is kind of like the operating system problem we had before. 30 years ago, in operating system, we have many different processes, different applications, and they are from different sources. Some of them may be malicious. And how can we isolate them? Now, technically, all of them running on one browser, we still need to isolate them. So one way to do this is actually the browser is not only one process. The browser has many different processes, multiple processes. There was a PhD or master thesis on this topic before. So the guy who was on the Chrome team, his dissertation was on how to. So imagine at the very beginning, a browser is like any other applications. You have one process. That's it. No matter how many websites you are visiting, you have one process, browser. Then how do we isolate them? If we want to utilize the OS level isolation, one simple way to do this is the browser itself has many different processes. And we may separate the tabs. One tab is visiting one website. Then that tab basically is running in one process. Another tab is visiting another website. Then that runs in another process. And the UI, what we're looking, is another process. So they are separated at the OS level. Then the browser, the JavaScript, they will make HTTP requests. to different websites. Then the websites, basically, they have their own OS. On top of that, they have web server, also a multi-process application. Then inside that, we run server-side script, like PHP. And if the website is compromised, then the website can directly send you malicious content. For example, malicious JavaScript. And the communication between them, we can also secure them just using TLS or HTTPS. That's basically the same thing. Now that's application level encryption and also confidentiality and integrity check for the application layer. The JavaScript, like I said, could be malicious. It can carry out all kinds of attacks against the browser. Because the browser is developed usually by C++, it has many issues. For example, we talked about heap security last week, right? So in heap security, we say the C language, malloc interface, delete interface, and also C++, the new and delete interface, they will create new projects on the heap. And there are use after free vulnerabilities, there are double free of vulnerabilities. For JavaScript, they do not have those kind of interface directly. Okay? In JavaScript, you cannot directly say, I create an object on heap using malloc. But in JavaScript, maybe all the big objects, they are always created on heap. So in JavaScript, you request a big object. Underlying the C code actually create some objects on heap. And then there will be heap-based security problems. Then even if it's high-level JavaScript code, it can utilize the bugs in the browser, and eventually, and that browser is a binary program on your system, and eventually attack the OS, get privilege escalation, all that is possible. Also, like I said, because JavaScripts, they are from different websites, one of them may try to steal things from other websites. For example, you are visiting your bank account, BOA.com, and at the same time, you are visiting another evil.com. Both of them are running JavaScript in your browser. So evil.com JavaScript may try to steal your information at BOA.com because they are running inside the same browser. So then what kind of security properties we want for web security? Basically the same thing. So all in security, we want the same thing. The first one is confidentiality. Malicious website should not be able to learn confidential information from my computer or my history on other websites. Integrity. Malicious websites should not be able to tamper any of my computer's data or my information on other websites. And also privacy. Privacy, I would say it's quite related to confidentiality here, but it's also a little bit different. So malicious websites should not be able to spy on me or my activities online. So to breach privacy, the attackers do not have to breach confidentiality. Even if you encrypt everything, there could still be side channel information to disclose your privacy, not necessarily breach the confidentiality. For example, we don't want a malicious website to trash my programs, my computers. So if I visit a website, it should not infect my computer with malware or change any of my files. So the difference for this is we sandbox the JavaScript. We isolate the JavaScript. So sandbox here is just basically another word for isolated execution. And this is a technique we have been using everywhere. We have been using this at the OS level. Two processes, they are isolated from each other. OS provides that level of abstraction to isolate them. In each process, they have their own memory address space. They do not see the other process address space. Also, in recent years, we have we have something like a trusted execution environment, TEEs. The idea is also just to isolate to sandbox. This is one of the most useful techniques in security. Basically, isolate. It's like during the pandemic. I mean, some people are infected. Then how do we stop the spread of the virus? We isolate people, right? It's the same concept. Then we do not want a malicious website to spy or tamper my information. For example, if I visit your website, evil.com, and evil.com should not be spying on my email, my Gmail, or what I bought on Amazon.com. And this is actually the defense for this is called the same origin policy. So all the browsers right now, they follow this rule, same origin policy. We will say a little bit more detail on this one. The idea is we can tell where a script is from. So going back to the very beginning of this semester, we have several lectures on access control. For access control, we have subjects, we have objects. Then we have access control rules. For each subject request to some objects, we say that if the rule allows the subject to do that, right? The same origin policy basically is a label or abstract attribute of the subject. And the subject here is JavaScript. And we tell this JavaScript, we label this JavaScript, you are from this website. This piece of JavaScript, you are from another website. Then the policy is the JavaScript from website A doesn't have the permission to visit any resources from website B. Okay? And this is enforced in the browser because the browser is visiting all those websites at the same time. Obviously, we want the data stored on the web server to be protected from unauthorized access. And for this one, we need server-side security. So a little bit more about the same origin policy. This is a policy enforced by browsers. Different browsers, they enforce slightly different policy here. The goal is one origin should not be able to access the resources of other origin. The subject here usually is JavaScript, or any subject can access resources. So JavaScript on one page should not read or modify pages from different origins. What is origin here? Origin means three things. For most browsers, origin means three things: protocol, hostname, and port number. Let's say here we are visiting a web page, the Wikipedia main page, right? Then the protocol here is just HTTP. The hostname is n.wikipedia.org. The domain name is the hostname. Then the port number here obviously is 80. It's implied here. Then we have another picture on this page. This picture is actually from a different domain name. It's from upload.wikipedia.org. Okay, so those two, they do not necessarily have the same origin. Depends on policy. For some browsers, we will consider they do not have the same origin. Let's say we have here we have example. We have some subject, some JavaScript embedded in this at this HTML. Okay. So the origin of JavaScript in this web page is HTTP 3w.example.com, then port number 80. So this part is just the path on the server. So this is not considered as origin. Okay. So at least so far, the policy, we do not consider this part of the origin. Then JavaScript at this web page will be able to access all the resources from this web page. At the browser side, we node both pages' content. We node the JavaScript from this page. We node all the resources from this page. And the JavaScript from this page will be able to access everything from here, because they are from the same origin. They have the same protocol, HTTP. They have the same origin, the host name, 3w.example.com, the same port number. However, it will not be able to, the browser will not allow the JavaScript from here to access resources from this URL. This URL has the same protocol, HTTP, the same domain name, however, doesn't have the same port number. Here we're using port number 81. So the browser will consider they are not the same origin. Other examples here, this is a different domain name. This one is the same domain name, however, different protocol, HTTPS. This one, different domain name. Just example.com, not 3w.example.com. Of course, there could be other rules, like the JavaScript from a parent host name, upper layer host name, will be able to access subdomains resources. For example, you have a JavaScript at example.com. Then that example.com JavaScript may able to access 3w.example.com's resources. So those are the details of the policy the browsers enforce. Different browsers they enforce different policies, but in general, we call all of them the same origin policy. Here are just more examples. You can take a look later. So like I said, different browsers, they have different definitions of same origin, and they also enforce different policies for different resources. Get, post, script, cookies, they may all have slightly different policies. So here let's take a look at other security challenges we face for web applications. But before that, we want to extend this to the database servers behind the website. Of course, there could be other servers behind a website, but usually there will be a database. So a simplified architecture would be the user side, we have browser. On top of browser, we run JavaScript. Of course, the JavaScript comes from the websites. Then on the web servers, we run server-side script like PHP, and the web server may talk to a database. There could be a separate database, and the database, usually we use rational database, but now we use more other database as well. Then we use secure languages to query the database in this case. So obviously, a code injection attack is still a big issue, not only for those binary software like browsers or servers. The code injection could also happen to high-level languages, like secure injection, like cross-site scripting. They are both code injection attacks. Of course, if you want to know binary injection, you can. We touch a little bit in the software security module and also after the software security class to do that. So the root cause for all code injection attack is the code and data, they are sharing the same channel. We do not separate the channels between code and data. When the browser says HTML, the browser in that HTML, there could be code, there could be data. There are text, right? That's data. There are anchors to point to pictures. There are data. There are also script. Those are code. They are mixed together. The browser cannot tell if this script is from the correct origin. The script maybe it's not supposed to be script. It's supposed to be data. That's why we have sanitizers. Do not allow you to, for any forms like that on website, do not allow you to input script there, right? To forbid you to do a script injection. Somehow we try to separate code and data channel. Of course, this problem exists in low-level binary as well. So I always use this paper as example. This paper is called English share code. So share code is a small piece of code, binary, to exploit software vulnerabilities. So in the software security class modules, you develop several, I would say, exploit, but you didn't, in this class, you didn't really develop share code. In the software security class, we do develop share code. However, the problem is plain text English. They could be malicious share code as well. In my share code module, I always use this example. You can say, here, this is an English paragraph. It doesn't read very good, but it's still readable English. There is a major center of economic activity, such as Star Trek, including the Ed Sullivan show. Okay, maybe that makes sense, but it's still English, right? But this English, if you disassemble this, if you treat this piece of plain text English as x86 instructions, they are actually meaningful instructions. So this is ASCII here, and this is assembling. They are meaningful instructions. They are pushing this. This is one instruction, another push, integer multiply, and jump, push. So this is executable code. But this is executable code for your CPU. And at the same time, if you only read this as English, it makes sense. It's English. And it's very difficult to separate this. It's hard to tell if this is code or just English, right? So I use this example to show that if we do not separate the code and data channel, you cannot really tell what is code, what is data. Yeah. Well, first of all, everything is data. Well, everything is code too, but the reason I say this is because this is meaningful code. This is really can do something malicious. Not, well, if you only look at the example here, probably you say, oh, it's not doing anything malicious. But the logic there, yeah. You can use this to build malicious code that look like English. So what this paper does is we have share code, then we have a share code, we have an English share code generator. Give me your share code, then go through my English share code generator. I make sure what the output is equivalent x86 instructions. However, now they read like some readable English. Yeah. So for example, in my software security class, I will ask you guys to do similar things, but we do not ask you to generate readable English. We will say you generate a share code that has only ASCII characters. It will not have long ASCII characters, something like that. Yeah. So the client side, the JavaScript will allow the web creators to run code they want in the browser, user's browser, when user visits the website. So the JavaScript can send HTTP requests using something like AJAX. It can manipulate web pages. It can manipulate cookies. So this is one example of AJAX. We can skip this one. Let's say I want to show you one example here, not this one. So because it can do all kinds of run all kinds of code, so it's very dangerous. That's why actually all the browsers will allow you to disable JavaScript or disable JavaScript from particular websites. But I'm not sure who wants to do that now, because all the web applications right now, they rely on JavaScript to run. Okay. The serious problem here is something called the cross-site scripting, and the cross-site scripting can basically bypass the same origin policy. The idea is this is a code injection attack. Okay, the attacker inject a malicious JavaScript into the web page viewed by a victim user. So the script will run in user's browser with access to the page's data. So it doesn't, the same origin policy cannot prevent this, because when the attacker injects that code to that web page, that piece of malicious JavaScript have the same origin as the page, so it can steal things. It actually happens within the origin. Let's say there are two types of cross-site scripting. One is called the reflected cross-site scripting. Attackers gets users to click on a specially crafted URL with script in it. Then the web server reflects its back. So in this case, the malicious JavaScript is embedded in the URL. The URL doesn't only have HTTP, and doesn't only have the protocol like HTTP, doesn't only have the host name. It can also have a lot of parameters, right? The parameter can be anything. The parameter can be JavaScript, right? So in this case, attacker will create a malicious URL, and part of that URL will just be a piece of JavaScript, starting with script, code, then /script, like that. Then someone clicks this URL, then this URL will be loaded into browser. Whatever is in this URL will be loaded in the browser, including the JavaScript in this URL. Then that piece of JavaScript will have the same origin with whatever the website you are visiting. Another one is stored JavaScript. So the attackers can leave JavaScript lying on a benign website, and when the victim visits that benign website, that JavaScript will be loaded and executed in the user's browser. Here, let's say some concrete example how this reflected cross-site scripting works. We have, let's say, we have a web server here. The web server, let's say, where's step one? Step one is here. Okay, this is an attacker. Attacker has a server. Attacker will craft, basically, this is a URL. The attacker will craft this URL. The URL is HTTP website, then search keyword. So far, everything here is benign. And after that, the keyword is script, okay? So the inside of this is some malicious script. Then the attacker will send just this URL to the victim. maybe using WhatsApp or whatever, or just a short message, send this whole URL to the victim. The victim click this URL. By clicking this URL, the victim's browser runs, right? The browser says this URL and say, oh, I'm supposed to visit this website. Okay. It's not thinking about the keyword, whatever search. First, it says, I need to visit this website. Then this browser will visit this website using this URL. The URL includes those keywords, basically, right? The keywords here is a script. Then this website, this is the code of the website. The code of the website will just print out HTML, print use searched for, then request or query keyword, then close this HTML. Then just give the result back to the browser. Then the browser will think. The browser, what does the browser get is this page. HTML, you searched for the script. The script actually was from the attacker. The attacker gave to the user through the URL. User gave that to the web server. The web server gave it back to the user. However, the browser doesn't know this part actually was from the attacker. The browser will treat this part of script from the website. And what this script do is it will actually, in this case, it will try to visit another attacker's website, in this case. Visit an attacker's website and also at the same time retrieve the cookie of the current web page. Cookie is a local thing on this victim's browser. Retrieve that and visit attacker's website. The goal is to send out the cookie to the attacker. As long as the attacker gets the cookie, the attacker can use the same cookie to visit this benign website and impersonate the victim. Does that make sense? Okay. So this is reflected cross-site scripting. In stored cross-site scripting, similar logic is just the attacker doesn't have to send the URL. The malicious script is stored somewhere, maybe in database, in some compromised web page or database. Let's say the attacker has a browser here, has also a server. The attacker sent a post message to this website. And this website has a vulnerability here. The website allows the attacker to store that script here. So in this particular example, this website looks like a forum. Okay. So in the forum, anyone can reply something, can comment on something, but you are supposed to comment in English. You can add pictures, whatever, but you are supposed to just comment with data, right? Not code. But here, the forum has a vulnerability. It allows that anyone to comment code. So they will comment a script and this malicious piece of JavaScript. Then when the victim visits this website, it will load everyone's comment. It will load everything on this forum page. And this particular item will be treated as code, not data. Okay, that's a problem, right? Then this piece of code will execute, and this piece of code will steal the cookie and send the cookie back to the attacker. So in this case, this script is stored on the website database. So this one is called the stored cross-site scripting. Of course, we can also do secure injection. The secure language. Well, there obviously there are two layers of translation. If you want to search something on the website usually do not directly give you a SQL query interface. Whatever they ask you will be used to build a SQL query. But as long as you know how it works, you may able to inject a SQL commands there. Let's say one example here. Okay, let's say our website runs the following code. The server will stores the URL parameter user in a variable called user rand, and then builds up a SQL query. The query returns the recipient's account balance. The server will send the value SQL to the database server to get account from the database. Okay, so this is PHP code. We have a variable called user. Then the user is actually retrieved from the HTTP post request user. So this is basically the underscore something is the HTTP, not HTTP, the PHP interface. So here we are retrieving the server. This is on the server side. The server is retrieving the user's post request. Then build this SQL query. The query is select account from customer where username equals to this. Then we just execute this query. Okay. So let's say if this is a benign user, the user wants to get Bob's balance or account, whatever, and the user has a permission to do so, the user will input user equal to Bob in the URL, right? This will be, actually this will be post. Okay. So then the constructed SQL query will look like select account from customer where username equals to Bob. Okay. This is benign, looks benign. And we'll only be able to get the Bob's account. However, the user can inject something malicious, like username equals to whatever, full, okay? Then this symbol, how do we call this? Okay, single quote, whatever, okay? So single quote in SQL language means comment? No, doesn't mean comment here, actually. Let's say, yeah, so the reason is because we have somehow we have oh yeah. I think what happens is this single quote is part of here. It's part of this. Single quote is here, right? It's already there. Then when the user input this full single quote or 1 equal to 1, eventually the generated query would be select account from this where username equals to single quote, full single quote. Okay, that syntax is correct, right? Username equals to this or 1 equals 1. Okay, because maybe we cannot find any username is full, but since we have all 1 and 1 equals to 1, it means we just simply return everyone's account information. So this part is basically what is the root cause of the problem? The root cause problem is, as a website developer, when I say username equals to something, I expect to say a username. And the username is data. However, this one, the attacker, gave me some username, and part of the username, this part, eventually becomes a part of the code, the query. It's not data anymore, it's code. So it's still a code injection problem here. Server side, we have the same issue. PHP, you can also inject the code. Let's say the EVA interface basically allow a string to execute as code. So you can do EVA results equals to 3 plus 5, it produce 8. You can also do EVA something and from user input. So this one is a HTTP GET message. So this is server-side PHP. You are using underscore interface to get what the user's expression is. Then user can basically execute anything here. One example, PHP server-side code for sending email. Let's say the email, we're getting an email address. We get a subject. Then we call system. Okay, this is very tricky. We call system mail email -s subject. So mail is another program on this server. System is a powerful API to execute another process or execute another program on the system. So if the hacker have so the example has some errors here. This is post. This actually is supposed to be get. Let's assume this is get because this is URL, right? So if the attacker posts this one, then email will be hacker@hackerhome.net. Then the subject will be user password will be redirected into full. Then the system basically will execute this PHP server-side code basically will execute mail to the hacker.home. Then where the subject will be full. However, the content will from the local user password file. So the attacker will be able to steal the password from the system, and the system will email the password to the attacker. So the problem here is the same. Whatever inside this system command or API supposed to be code or commands, right? Commands, I also think them as code. But the user input should just be data, should never be used part of code. But here we somehow inject that as code, and we're able to steal password. Okay, that's all I have for web security. Like I said, web security is a huge topic itself. I don't think we have a web security course in the department right now. We used to have. The professor offered multiple years. Then the professor actually left. So right now, I don't believe we have a web security course. But if you want to learn web security, there are a ton of teaching tutorials online. All this capture the flag competitions. There is a big module for web security. For all the CTFs, crypto, software, software basic binary, then web, there are big categories. There are many challenges for them. Any questions? Okay, cool. So Wednesday we will have a review for the semester's class, and I will give you guys some preparation guide, same as midterm. I plan to have the final a little bit easier than the midterm, because most of you struggled in the midterm. And also I'm trying to be generous in grading homework. But AI violation is still very serious. I take that seriously. If there's any violation, then you get a penalty. As long as you do not have AI violations, then I can make the exam a little bit easier, so you can get a higher grade. Okay, cool. See you Wednesday.